What? Hey guys, can I get a sound check? Let's see. Can you guys hear me? Can anybody hear me out there?
Yeah, we can hear you.
Alberto, or did somebody say something? You guys hear me? You okay, great. Thanks, Nathaniel. Let's see, what am I doing? Dub, 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 dub. 4203. Where were we? We were in short channel effects. Any questions, guys? Anything I can talk about before we start talking about the class stuff? Okay. In that case, let's see. Let's dig back into the second order effects for MOS transistors. So we talked about the body effect. Where were we at? So we talked about the body effect, right? Body effect. Okay, so sorry, trying to get back to it. So, you know, we talked about, now we're still talking about what the second order effects. Watch what I say, because some of the stuff is second order effects when the transistor is on, and some of it is second order effects when the transistor is off, and some of it is kind of in between. So all this stuff, you know, this electric field dependencies that we talked about, again, was all about when the channel is on. Back here is all about, this is all when the transistor is on. So now what we're talking about is threshold voltage effects, which is sort of when the transistor, some of it has to do with threshold voltages with the amount of current that you get when the transistor is on, and some of it has to do with the break point. So the threshold voltage affects your final current, that affects your break point from when you go from saturation, from linear to saturation, and then it affects where you actually turn on. So it can also affect your leakage current. So last time we talked about the body effect, is where we left it off. And basically that's an effect, you see that all the time, the body effect is when the source and the substrate, or the source and the body of a transistor, are not hooked up to the same voltage. And you see that a lot of times, and I say in both NMOS and PMOS, but what it basically means is when your source of your NMOS, for example, you know, this sort of second transistor in your NAND gate is a good example. When the source is at a higher voltage, or can be at a higher voltage than your substrate, then this threshold for this device gets higher than what you would expect from when the source and the body are connected to the same thing. And that tends to reduce your on current for this device. So That's like a body effect. I see it all the time. I have dealt with it all the time. It's very like normal. The second thing, which probably you see less of, is something called drain-induced barrier lowering. So what does that mean? So so one way to think about it is, especially when, again, just drawing our transistors. This is the oxide, this is the poly. So, around here is the channel, and this is the drain. And let's say this is the voltage of the drain. So your channel is, around here. So what happens is, one, we haven't really talked much about this. I think I mentioned a little bit, but one of the things that happens is that in the second order effects is that this model where IDS is equal to 0 at VGS less than VT, this is no longer correct. If that was the case, if we looked at a graph like this, which is VGS versus IDS, the current would go, something would happen here. So this is exponential and linear. You would get to here and you drop off to 0. But as you can see, what happens is your current does not go to 0, but starts sort of dropping off. So you have this region, which is known as the subthreshold region because you're below the threshold value. So this is 0 VGS, this is VT. So in this region, you still have a current flow, which is the subthreshold value. And then when the VGS, even when the VGS is 0, when the gate is completely at 0 volts, this is for an NMOS, you still have some current flowing through the device. This is the leakage current or the off current. It's a very small number. We'll talk about this in a little bit, about this small off current. But what we're talking about here right now is this drain-induced barrier lowering, which means that, and that relates to that, depending on the drain source voltage, that subthreshold current could actually be larger or smaller. So the larger the drain source voltage is, the higher that drain source voltage is, your subthreshold current, it ends up being larger than at a lower value of VDS. Okay, and the reason that's important, so the device transistors in a digital process don't spend a lot of time in this region, time-wise, right? We're either at a VGS of like a VGS, in this case, I don't know which process this is for. Let's say this is for a 1 volt VDD process. So a digital transistor typically is either operating here when the gate source voltage is a binary 1 or a 1 volt, or it's at 0. So it doesn't really spend a whole lot of time in between. I mean, it's basically as it's on, it'll discharge the capacitor and turns off and comes down here. So what this curves, the important point is the asymptotic value of the curves when they hit VGS of 0. And the upshot is, because of these different drain-induced barrier lowering, this effect that the drain has on the channel, you end up with a different leakage current on the transistor when the drain is high than when the drain is low. So when the drain is at a high value, in this particular case, the leakage current of this transistor is 27 nanoamps. And when the drain source voltage is 0.1, you get a leakage current of 2 nanoamps. And so, I mean, that's like a huge, that's obviously a factor of 10 difference in leakage current between those two drain source values. So this is when the output is a logic 1, and this is the case when the output is, close to a logic 0 with a VDS of 0.1. So you can see in both of these cases, the leakage current for the VDS of 1 is going to be higher. So so anyway, that's like the upshot of this, is that you end up with a different subthreshold current operation. Okay, so that's drain-induced barrier lowering. Okay, and then finally, there's these short channel effects that as you, I'm just drawing the same thing, I just copy it over. Okay, the next effect that happens, again, has to do with your drains, is that as your transistor widths get reduced, remember that you also have a depletion region around your drain. So this tends to make it makes it, as this L is reduced, it makes your threshold voltage go down, because it's already like the electric field from the drain is sort of partially, it's helping, I shouldn't say it's turning on the transistor, it's going to help the transistor turn on faster, meaning that depending on the actual length, so let me put it this way, if you're in a, you draw a transistor with a length of 65 nanometer, it might have a threshold voltage of, I don't know, 0.3 volts, and a transistor with a length of say 100 nanometers might have a threshold voltage of 0.4 volts or something. I don't know exact numbers, depends on the process, but basically the lower transistor lengths tend to have a lower threshold voltage. Okay, so those are the threshold effects. Now going back to the leakage effects, again, we're looking at these the subthreshold region. If we had the ideal model, again, if in the ideal model, IDS would just go to 0 when VGS it's less than VT, which is no longer the case. Okay, that does not happen. But you basically end up with some amount of leakage through your transistor when it's off. And there's a few different leakage sources. So let me just sort of again say this. I think I want to say it one more time. So let's look at what we're talking about here. So when's a transistor? Okay, so let's say here's a CMOS inverter, and let's say it's representative of all the other circuits. All the other circuits, NAND gates, NOR gates, exclusive OR gates, and so on, just look like somewhat look very similar to this. They have the pull down network and you have a pull up network, etc. So what are all the different operating things that this guy does? So let's say I have an input and an output, and they're changing as a function of time. I guess the input's changing as a function of time. Say my input is gonna have, it's gonna do this. And then it's gonna just, basically it'll be a pulse on my input. So this output is driving, you know, another bunch of gates, whatever it happens to be wanting to do it. All these guys are gonna look like, if you sum up all the inputs, they're gonna look like some capacitance hanging off of here. So as we'll see, the output is gonna be, you know, it's inverted. So when the input, so red is in, purple is out. When the input is low, the output's high. When the input goes high, the output's gonna start going down. It'll look like this guy turns on and discharges his capacitor to ground and stays like that until the input goes low and the output goes back high. Something like that. So that's the input versus output curve. Okay, so when there's the on currents matter here and here. Why do they matter there? Because here the NMOS is off, right? Here the VN is 0. So VGS for this NMOS is 0. So this guy's off. PMOS is on, and it's keeping this value at this output as 1 volt. But because this is purely capacitive, this guy's off, this guy's on. There's no, it's on, but there's no place, once it's discharging or charges this value all the way to VDD, there's no current flowing through it. So let me draw that. So let's say if I just draw it like that, right? It has a certain VGS, so VGS of say 1 volt across it, right? So let's say this is 0. It's easier to show you guys in the NMOS case because that way we won't get us confused. So let's think of here when VN is high. Okay, so let's look at it here. When VN is, so this is VDS, IDS of the transistor M1. Okay, so this is when VGS is, so this is VN is equal to VGS of VDD. So the highest value. And let's say VDD is 1.8 volts. That's what it's going to look like in your projects. So as soon as you say my input is VGS, you're going to pick one curve that this transistor's current can be on. It's going to be on, right? The transistor is VGS of 1.8 volts is definitely larger than, let's say the threshold voltage, I'm just going to give it to you as like 0.7. So that's definitely greater than 0.7 volts, and the transistor is on and it's following this curve depending on where the drain source is. When this guy just up here, as soon as this guy becomes 1, right, up here, let's say it turns on very quickly. Initially, the drain source value here is out here because you had a 1 on the output. You had a 1 here or 1.8 volts here. So that's the drain. Source is at ground. So initially, your drain source value was at 1.8. So initially, you were out here, basically here. When this guy just turns on, the output is still high. Okay. as you discharge, then it's going to have a bunch of current right here. That point, this guy's going to have an IDS value of beta over 2 VGS minus VT. I mean, if it was, just again, this is simplified ideal current, right? So it's going to have an IDS value with that current, with that IDS value, it's going to discharge this node to ground. It's going to be basically pumping current. So it's going to look like, initially, it's going to look like a current source discharging a capacitor with a certain IDS. So this is just this capacitor, all this load. Okay, so, and this basically is going to reduce the voltage on this node. So what it's doing is it's really reducing its own drain source voltage at the same time. This node is going down. This node is going to start going down. So it means the drain source, the VGS on this guy stays constant because it just stays that as, you know, at a 1.8 volt, but the drain source voltage is starting to go down. So it goes down, 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 down. At some point, it goes from a saturation, then it goes into linear. And at some point, it'll get here at when the output goes to 0. So here, when V out goes to 0, this transistor has a gate source voltage of 1.8. It is on, but there's no current flowing across it because this guy is at ground and this guy is at ground. Okay, so there's no current flowing across it at this point. Once it discharges this down. So the period where the on current of this transistor matters is just this period, sorry. So there's a rise time. Typically your rise and fall times are only just a small portion of your total waveform. So this will matter. And then the PMOS current matters in this region, the on currents. So those, basically the on currents will decide how fast you transition from low to high and high to low, okay? So after that, your on current doesn't matter, just in these transitions. Whether your output is high or low, again, your on currents don't matter. What matters is your off currents. So for example, look at this. So this guy is on in this case. So here we said this guy's on, this guy is off, this guy's on, but no currents flowing through it from the capacitor. This guy's off, so we should get no current flowing. But we have leakage currents. And let's say this was the leakage current for a PMOS, which is, it's kind of going to look like this somewhat. And so this PMOS now, because the output is low, the NMOS drove it low. So this PMOS effectively is going to have a large VDS across it. Its gate source voltage is going to be 0. So it's going to be kind of sitting here. It's going to have a large VDS and it's going to have a VGS of 0. So it means that it'll have a very small current. So this whole time, the PMOS is going to have leakage current with VDS is equal to 1.8 volts. Okay, and that current is just going to go from here, whatever that is 27 nanoamps per micron. It's going to go through here. This guy is on, so that current will just go from power to ground, this leakage current. So here you'll have a leakage current, and here you'll have the leakage, you'll get the vice versa. The PMOS will be on, but we'll have a very low drain source voltage or 0 drain source voltage. The NMOS will be off. You expect it not to have any current, but it'll have a leakage current with a large VDS, so with a VGS of 0. And so it'll have a current going through. So this will be I, NMOS will be leakage current. Okay, so that's what happened. So now the leakage currents, look at the on currents for transistors. These are like sort of very rough numbers. But when we're talking about on currents, where's my on current? And this is just one example. But we're talking about, it doesn't say, does it say what transistor size? It doesn't quite say the transistor size, but you know, you're talking about, it's in the, you know, it's in the milliamps. This is like where the on current is. I think this seems like a pretty big number to me. Say it's in the milliamps. So let's say, sorry guys, my dog is making noises. Let me close the door. Where were my notes? Okay, so typical, oops, typical.
Professor,
Yes.
what do you mean by this leakage current?
I'm sorry,
I
can you
didn't
say
get-
that again?
What do you mean by the leakage current? I didn't get that.
Oh, what is the leakage current?
Yes.
Okay, so basically, like this is, remember, let me take a step back. So so this is going way back. So we have an NMOS. It's always easier for me to think about an NMOS. Okay, it has it's got the body. So it's a 3-terminal device. So it means that if we want to look at the relationships between the current and the voltages, we really need 2 graphs. Okay, so we need, one of them would be we need two-dimensional graphs. One of them is VDS versus IDS, and the other one is VGS over IDS. Those are the 2 graphs we need. So in one case, you're going to hold, in this case, you're going to hold VGS constant and sweep VDS. So that means you're going to get a series of curves of VDS versus IDS with different VGS values. And then the same thing, this is exactly the same device, but to be able to represent VGS versus IDS in a 2-dimensional graph, you also need different, you need to hold VDS values constant. So in the most ideal model, basically, if I do this, I'll get something like this. So for all VDS, sort of, I would get, is that true? Let me see. VGS. No, basically for different VDSs, I would get sort of different values here. Okay, depending on where I get. So, and then the equations are IDS is equal to 0 if VGS is less than VT. So means as if VGS is less than this threshold voltage. So this is the ideal model. The ideal model says the threshold voltage is constant. And it says that the current IDS is absolutely 0 if VGS is less than this value of VT. So that means that when the transistor is off, there is 0 current, IDS current flowing through it. So in this case, a VGS of less than VT would show up as on this curve, it would show up here. So any VGS less than VT would just have IDS of 0 regardless of VDS. Okay. And then IDS would have some values, beta VGS minus VT minus VDS over 2 VDS and beta over 2 VGS minus VT squared. So this is if VDS is less than VGS minus VT and VGS is larger than VT, and this is VDS is larger than VGS minus VT, VGS is also larger than VT. Okay, so this would be the transistors on. This is transistor off. So Mohammed, are you with me so far?
Yes, yes,
Okay.
Professor.
So the first level model is that the transistor is off if you're below, VGS is below VT. This was true back in the day when, you know, transistors were physically large and all that stuff. What leakage current says is this is no longer, it's no longer true. What it says is when VGS is less than VT, we will get, whoops. So this is the no longer true. What you'll get is some I leakage. Even when the
Okay,
transistor
got
is
it.
at, you got, sorry, go ahead. Sorry, what'd you say?
Yeah, got it.
Got it. Okay. So it's just basically that's what it says. And then there's a bunch of complications. Like this will be a function of a bunch of different things. And that's what we're going to start talking about. And so the reason I was going into this really sort of maybe I confused you guys, but what I was trying to get to is why is leakage important? Because when you're looking at the on currents, you're talking about 1 to 10 milliamps, say, let's say per micron. And then let's say typically this is on current. And then when you're talking about leakage current, you're talking about IDS as, I don't know, 20 nanoamps per micron. So this is times 10 to the minus 3 milli. Nano is times 10 to the minus 9. So this is like 6 orders of magnitude less value between the leakage current and the on current. Okay, so yes, there is this current flowing when the transistors aren't switching, but it's really, really small. So why is it important? And it's important for 2 reasons. One of them is that the total amount of time the transistors are on, and you know their on current is really active, it's very small. It's only during the transitions from low to high and high to low. The rest of the time, even when the transistor is on, because you know if the pull down network is on, the pull up network is off. So theoretically, there should be no current flowing through this on transistor. So you know, after it's done transitioning, this on current doesn't really mean anything. Okay, so it's just, and then vice versa. So the whole time, the on current is only active during the transitions. The leakage current is active during all the other times, which are relatively more frequent, much more frequent than the on time. So when you think about it, the thing that makes the most transitions in a chip by definition is the clock. So the clock has, you know, it's basically transitioning like this. The most any other thing will transition is at, let's say we had data, it's only going to typically transitions at the rising edge of the clock because you have flip-flops, etc. So data is even going to have lower transitions. The fastest data is going to have lower transitions than the clock. And in fact, most data only transitions, some of the time, might not do. So data fastest, data, I don't know, active, let's call it. And honestly, most of the data is just going to sit there and do nothing most of the time. So remember that in our chip with billions of transistors, most of the transistors are just sitting there. They're not like switching. The problem is they're always leaking. Okay, even when they're not switching, they're leaking. So yes, the on current is significantly higher than this leakage current, but this leakage number of this 20 nanoamps or whatever it is, so it's in the nanoamps or whatever it is, gets multiplied by a very big number, because at any one time, there's only a small percentage of the circuits that are switching any given period, but most of the circuits are going to be in this situation. So the leakage current does matter. When we first started with CMOS, one of the things we said when we were talking about the logic family was that there was no DC current flowing. And that was true for many, many years, and what really sort of made MOS what it is now as the most prevalent technology. But it's no longer true. Now the leakage currents are significant. And as you'll see later, the power consumption between when the device is operating and the leakage, it's like maybe sometimes in some of the bad nodes, maybe only like a factor of 2, or maybe, typically maybe it's a factor of 4 to 1 or something like that. That's correct. So Tunji is asking, is this due to the nanometer process? And it is correct. As the technologies have gotten smaller and smaller, this leakage current has gone higher and higher. Okay, so for a variety of reasons. So like for one of them we just saw, which was what we said was drain-induced barrier lowering, right? Just this happens when we have, we talked about this, when the transistor is small, the drain is really, the electric field of drain is interfering with the channel. So in this case, look at the leakage current ends up being, a factor of 10 higher in leakage current than it would have otherwise been without this effect. Okay, you got to get a little bit used to this curve. So this curve is VGS versus IDS. So it's sort of supposed to be this, but these curves still confuse me because you usually don't look at it this way. But so it's the same thing, VGS versus IDS, but it's a log curve. So your on value versus your off value, while there's like a significant difference, you're talking about milliamp versus nanoamp, but in the graph, because it's log, those sort of looks next to each other. But this basically is whatever 6 orders of magnitude, 5 orders of magnitude higher. Okay, and it's really zoomed in to this area around the threshold value, so you can see that it doesn't turn off. So even if I was going to make this, even if I was going to make this a log scale here, if it really went to 0, it would just it would sort of like this whole curve would move down to wherever 0, I guess, I don't know, yeah, wherever 0 is. I guess it never quite gets to 0 when you do log, but you see, I guess hopefully you guys see what I mean. But anyway, this is because of the nanometer process. So here's this drain-induced barrier lowering. And so now we're going to talk about the different leakage effects. Okay, so what is happening. But what I wanted to sort of, the reason I made this tangent here, I just wanted to make sure you guys were clear on and Mohammed's question helped about what leakage current is and why is it important. Although, we're talking about really small numbers for each transistor, when you sum it up against all the time the transistor spends in either in not transitioning, which is, imagine that's most of the time, multiplied by all those transistors out there, it all adds up to a number that is close. It's not exactly the same, but it might be like a fourth or an eighth the off current. So that's a lot of trouble in a lot of circuits, because you're like, again, like imagine if your cell phone was just like the difference, it was like always burning power, like when it was on and you were using it to talk, your talk time is probably what, I don't know what it is, maybe 2 hours, 3 hours, I don't know what it is, but it wouldn't be really usable. So you have to find ways to get around this problem. But first we're describing the problem. So these are the main leakage sources. There is the subthreshold current, which is when the transistor doesn't quite turn off. And this is, again, this effect that this guy does not drop off when it gets to the threshold, but there's still current. And there's current even when VGS is 0. So this is the dominant leakage effect. But in addition to that, there's actual, so that is this leakage. This is the sort of the subthreshold conduction. But you actually get leakage current going into the gate, because your oxide thickness is so small. You're talking about, we're just talking about really just a few atoms of silicon dioxide. So you can get basically tunneling current through the gate. So you actually have a leakage current through the gate. And then there's the leakage of the junctions itself. So remember that the drain, whoops. The drain and the source are PN, or reverse bias PN junctions. So the substrate is P. So all around here, away from the channel, these look like reverse bias PN junctions. And if you guys remember, a PN junction is a diode. And if I draw the diode, this is, when you're in reverse bias, you're sort of over here, and you get a current of minus, so whatever is that I sub S, whatever is the leakage current across your diode, and you'll basically, that's what you'll get. So you'll get current going from drain to source, that's the subthreshold conduction. You'll get current going from the gate to your source or channel, and then you'll have current just going from your drain or source to the substrate, which is this junction leakage current. It turns out the subthreshold current is the most significant one in modern processes. And, it's got a complex equation. So I don't really memorize this equation. I think only one thing is important and very important is this approximate equation. Okay, that we got this. Where is the S here? So the S term, so this is the drain source current. and you have some baseline multiply that's by 10 to the power of something and 1 minus exponential of something. And this S denominator is very important in the operation of this value. Okay, so the critical thing about this S, and the one that I do remember, is at sort of room temperature, typical temperatures, this is 100 millivolts per decade. What does that mean? And why is it important? To me, or a rule of thumb, is that whatever your current is when you're at the threshold voltage, every 100 millivolts, it'll get divided down by 10. So if your threshold voltage is at 0.3, at 0.1 VGS, sorry, at 0.1 VDS, okay, you'll have a current, sorry, VGS, sorry guys. So at your current is whatever it is at VT, okay, VT is 0.3 volts. At, just write it down so I don't confuse myself. So say VT is 300 millivolts. And I leakage at VT is equal to 300 millivolts is I sub X, okay? Then by the time you get to VGS of 100 millivolts, sorry, yeah, VGS of 100 millivolts, your I leakage ends up being, so it ends up being, so notice this is 200 millivolts below this. So your leakage current is reduced by, a decade means 10x, by 10x every 100 millivolts. So at this point, you are I sub X, your leakage current is I sub X over 100. Okay, and by the time you get to a VGS of 0 volts, your leakage current is I sub X over 1,000. Okay, so what does this mean? And this is an absolute number. Okay, so it says that if I made my device, so let's say everything about this device was exactly the same, but I had two flavors. I had a flavor that had a VT of 300 millivolts, and I had a flavor that had a VT of 500 millivolts. So say everything else being the same. Say now VT is VT1, VT2 is 500 millivolts. So notice that again, the same value holds. At every 100 millivolts below, my leakage current goes down by a factor of 10. So by the time I get to VGS of 0, I get I sub X over 10 times 10 times 10 times 10 times 10. The lowest I could get in this guy was I sub X over 10 times 10 times 10, or I sub X over 1,000. Here, I can get to an I sub X of, what the hell is that? 100,000? Okay, so basically it's saying I can reduce my leakage current, my subthreshold leakage current significantly by just making, if everything else was equal, by making my threshold voltages higher. Okay, so here's the device with same, everything the same, 500 millivolt threshold voltage versus a 300 millivolt threshold voltage. Okay, you guys follow me there? So why don't we just crank up the threshold voltage to kill off this subthreshold leakage? Well, the problem is now we've got a trade-off versus the on current. So the on current, again, we know it's not exactly this, but again, roughly we have for an on current, the lower the threshold voltage is, the more on, again, all things being equal, the lower the threshold voltage is, the more on current I get. And significantly more. And maybe it's not square law, maybe it's something else, but it's significant effect on the on current. So that is the problem, is you've got a trade-off between the on current. The on current decides how fast you're transitioning between 0 and 1, which means how fast you can operate your circuits. Okay, so the lower the threshold voltage, the faster you can operate your circuits, because the more current you'll have to charge and discharge these capacitive nodes. But you're going to have to do that at the expense of leakage current. And that's sort of, again, sort of all things being equal, more things go into this, but that is what you'll see a lot, is people are, so in a nutshell, what's going on? In a nutshell, maybe it's not such a nutshell, but what's going on? So node, the dimensions are shrinking. Why are they shrinking? To get more transistors on the same chip. Meaning what? Meaning price or cost per operation goes down. Okay, so that's a big motivation in shrinking your dimension. Okay, and then the other thing is, if you can get more transistors on the chip, same chip, you get more functions on the same chip. A big part of speed reduction in your electronic circuits is going off chip and coming back on chip, right? So if you need to go off chip for a memory interface, that's always slower than whatever operations you do on chip, or if you're going to need to go on a bus, etc. So those are the cost and overall system speed are the reason dimensions are shrinking. As the dimensions are shrinking, electric field magnitudes go up, significantly up. So, and that causes, we notice that causes all sorts of problems. Electric field magnitudes are messing around with your on currents or the functionality of your devices. So what do you do? You reduce your supply voltage to reduce electric fields. So like, for example, a 1.8 micron process it's got a 1.8 volt VDD. A 65 nanometer process has a 1 volt VDD. Okay, so you start reducing the supply voltages. So this reduction of supply voltages reduces on currents. Why? Because to first order, it's VGS minus VT squared. So and then VGS is VDD. Okay, that's when you put a logic 1 on an NMOS gate. The highest you can get VGS is VDD. Well, guess what? Now you reduced your VDD from 1.8 volt to 1 volts here, and you significantly reduced your on current, which means you significantly reduced your speed. Okay, so we reduce our speed. What do I do next? I'm going to reduce my VT to make up for this, to make up for reduced VDD. But guess what? This increases leakage current. And where we are is do your best to balance all of the above. So in a nutshell, that's what's going on. As you're getting smaller and smaller, our power supplies were going down. They start reducing the threshold voltages. And at some point, we started having some significant problems with leakage current. And that's kind of how we are. Sometimes they've backed off. If you looked at, supply voltages, they're not going really significant lower. Yeah, so Tunji is saying when the leakage current increased power consumption also increases, that is correct. So power consumption increases when nothing in the circuit is happening. Okay, there's two types of power consumption. One of them is all the circuits that are transitioning, and then there's a power consumption of everybody else is just sitting around. And that the amount of power consumption of everything that's sitting around is increasing. And so you've got to we'll have a whole lecture on power consumption, and it'll be an important part of your report study on comparing the processors. But you'll see kind of the effects that leakage has, and so what are the figures of merit, et cetera. So both now used to be 20 years ago, leakage current, you wouldn't really even worry about it, except for, if you were making a pacemaker or something like that, some analog circuit that needed to have a battery that lasted 5 years. But now you care about it even in your microprocessors and FPGAs and so on. Okay, so that was the subthreshold leakage. Then, I'm not going to get much into this. This is like something that happens. You get, again, gate leakage, and there's really not much to say about it except, do not assume. So basically, you'll get some leakage going into the gate. Most of the time, again, notice that. So let me draw the full circuit. So a simplified but full circuit. Let's say, you've got an inverter. If you've got the gate of something, you're driving the gate of something else. We're talking about leakage current into these gates. But it's kind of happening in parallel with the leakage current through the subthreshold leakage. And we're saying this is much higher than this gate leakage. So typically you don't really, you don't really care about, typically significantly less, let's say, the gate leakage than the subthreshold leakage. So typically you don't really care about it except when these gates get very large. And there are like a few circuits, and I'm not gonna, right now it's like they're too complicated to get into. Like, I don't know if you guys have heard about like phase lock loops on chip to generate clocks, etc. Those circuits have large capacitors for their filters and so on, and then you can get into trouble with gate leakage. But most of the time it's lower. I think it's just important for you guys to remember that there is gate leakage, but it doesn't get into the calculations much. The other types of subthreshold leakage is just the drain source junctions and the fact that they're reverse bias junctions, etc. And again, you get some, you get the diode, leakage and so on. But again, it ends up being fairly small. compare, you get the band-to-band tunneling and all this stuff. Most of the time, and these things ends up being fairly small, and you can just worry about the subthreshold leakage. And really the thing to remember about the subthreshold leakage is that it is it has this reduction by a factor of 10 for every 100 millivolts you go below the threshold voltage. So this relationship that the higher the threshold voltage of a transistor is, the lower its leakage current is, but then the lower its on current for a given supply voltage. Any question about that? Okay, so finally, sort of final effect is, let's talk about, so we talked about, these are the on-off currents, effects of electric field, threshold voltage variations, etc. So another second order effect is, notice again, I'm gonna write this down until you guys are sick of it, but just something so we had this IDS value, which was 0 when VGS was less than 0, then less than VT. And when VGS was larger than VT, we had some equations for on current. But we were just looking at the effects of voltages on the current, but there are other effects on the current. So we have one of them is voltages, but the other one was actually the temperature of the chip affects your current as well. And it is a pretty big effect. Okay, so what happens is, as the temperature increases, we have two effects that are sort of fighting with each other. I guess there's no way but to repeat this equation. So again, this is the first order equation. VGS minus and this beta has a mu and Cox term. So this is all for NMOS in saturation. Okay, so we got two effects here. One of them is the mobility at higher temperature. The mobility tends to go down. So remember that the mobility is a ratio of, V sub n is mobility times the electric field. So mobility is what tells you how fast a electron will go given an electric field. Okay, so this mobility goes down with temperature in the typical temperature ranges we're dealing with. If you take a semiconductor class, you'll see that it's actually does all sorts of funky things, but sort of most temperatures that we're dealing with are, say minus 20 C to 85 degrees C, typically. This is where we live. This is where most of our chips live in. So in this range, mobility goes down with temperature. So that's one effect. But there's an effect that sort of goes in reverse of that, is the threshold voltage also goes down with temperature. But when your threshold voltage goes down, that actually increases your current. So, there's this fight between those two. But in the end, what happens is your on current always goes down with temperature. Okay, and your off current increases with temperature. So your leakage goes up, your on current decreases. Both of them are bad factors because we want our on currents to be large so we can switch as fast as possible, and we want our leakage to be low so we don't burn unnecessary power. So high temperature is bad from that point of view. Okay, or So let me put it to you another way. Well, so how should I put it? Well, I don't, let me get into this later, but it's high temperature tends to lower the operating speed of your chip and tends to increase the leakage current, but which increases the power consumption, which increases the temperature, unfortunately. So when you see your chips, you're trying to, you guys are maybe, I don't know if you guys are any gamers in the room, but that's one of the things you guys have probably seen or heard of is when people use, they take regular processors and they do liquid cooling or those kind of things to keep the temperature of the chip or the processor down so they can operate it faster, so they can overclock it. That's what they're doing. Is the higher the temperature that you have, your chip is slowing down, and so you want to operate it from a speed standpoint, you want to operate it in as low a temperature as possible. Okay, so this is not a voltage sensitivity, it's a temperature sensitivity. Any questions about that? I won't get into the details of what, but let's see, what else do I want to say? Okay, so let's talk about so this is another effect. So let's say you're designing a chip. Okay, so we talked about, we'll have a certain V threshold voltage of 500 millivolts, say, okay, for a process. What does that mean? Well, probably like silicon chips are, we talked about how expensive each factory is. We're talking about, $5 billion, $10 billion per factory. We're talking about, 3 nanometer, 5 nanometer feature sizes. These are some of the most precisely manufactured components that humans manufacture. I don't know what else is sort of high level of precision. If you're talking about something that we can make down to 5 nanometer control of aligning something with another, so very precisely made up, created. But they're like any other manufacturing process. When you start making more than one device, you start seeing variations in what you create. Okay, so when you're talking about, when you're giving a single number for a threshold, it means that this is a nominal value. So for example, if you plot a distribution, so number of transistors, say, or it could be number of chips, etc., some distribution. So this is a histogram, okay, of a population. What it'll really look like, it won't look like this. It won't look like not all of them are going to end up at exactly at 500 millivolts. In effect, what you'll get is very typically, you'll get, just like a lot of other things in life, you'll get a Gaussian curve, okay, where the majority will end up, at the mean value will be 500 millivolt. And, then you'll have a sigma around this, and, maybe it'll be, I don't know, your sigma might be, I'm just going to make something up. It might be 50 millivolts. Okay, and you're sort of guaranteeing that, by the time you get to like 9 sigma or 6 sigma, oops, 9 sigma, 6 sigma. You're not going to be too far off of this thing, but it basically, I mean, maybe I'm overstating this 50 millivolts, maybe it's 25 millivolts, but there is a distribution around your threshold voltages just from a manufacturing standpoint. Okay. Typically, the way this looks is some chips will end up, so what'll sort of end up being is something like this. So this is, there'll be different sort of wafers or chips. It depends on the manufacturing problem. So say this is wafer 1 and wafer, wafer 1000 might look like this. And, wafer 5000 may look like that. And stuff in between. Okay, so this means that when you're actually simulating, when you're designing, you have to take into consideration this variation in threshold voltage. Okay, so because you want something that's manufacturable, you don't want to make one of something, you're trying to make millions of something, ideally, or thousands of something. So you have to worry about these variations. So the way, when you're doing, and I just wrote V threshold here. I could have easily said beta. So mu n Cox, it's going to have its own variations. The actual transistor lengths and widths might have, just coming from a printing process, might have their own variations. Lots of other things. Basically, everything has variations. Okay, but when you're doing analog design, things get pretty complicated because you have a lot of different parameters that you're worried about. You're worried about the gain, you're worried about the bandwidth, etc. Now, fortunately for logic, you're typically only worried about power consumption and speed. And so what they do is they basically, the fab sums up all the variations that affect speed, for example, and sums it up in one set of variations. So what you'll get is you will get a bunch of different transistor values. You'll get in your SPICE stacks, you'll get typical, so SPICE or other simulation model. You'll get this from the fact. You'll get the typical value. What is that? Why is it called typical? It means the NMOS is typical and PMOS is typical. That's your sort of your nominal value. And then you'll get fast means low or so high. I'll just say, I wouldn't say low VT because it's not just VT, but they've added a bunch of stuff in. So it's really high on NMOS, high on PMOS. That means so the higher the current is, the faster that device is basically is able to transition its output. Then you'll get slow. So that's low on NMOS, low on PMOS. And then you'll get fast slow, which is high on NMOS, low on PMOS, all the permutations, and slow fast, which is low on NMOS, high on PMOS. And so these are called, the corners, process corners. And if I was gonna plot them out, it'd be looking like this, okay? So you'd end up with, you'll get different transistor models. You'll get both transistors being fast, the NMOS being fast, PMOS being slow. That's fast, slow, 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 which is a slow NMOS, slow PMOS, and a slow NMOS and a fast PMOS, and then we get typical. Okay, these will be some value, and the foundry is going to give you these models. And what you'll have to make sure is that your circuit will work under all of these conditions. Otherwise, what happens is, let's say you design your circuit to only work here. That means every wafer you get, what the foundry is telling you with these models is that there is a possibility with the variations in their process that they might produce stuff out here. That means every wafer you get that's out here, you might have to throw away. Okay. And in effect, what's happening sometimes is when you see like different speed grade parts that you'll get from Intel, I don't know if you guys are into this or not. Again, mostly comes out with gamers, or you'll see like different speed grade. I guess you'll see them in computers, etc. What means is that the processor company is trying to not to throw away these parts that were outside their major speed grade. They're still going to sell you this stuff, but with a derated speed grade, because they want to save these parts. They don't want to throw them away wherever those speed grade parts are. It'd probably be over here. They don't want to throw these guys away, so they'll selling it to you at a lower price at a lower speed grade. That's what it sort of comes down to. So the stuff that makes for a fast, like I said, it's all the foundries wrapped up a bunch of stuff into the fast corners. It's basically short transistor lengths, low VTs, and thin T oxides. Okay. And so anyway, so that's the upshot is you have to worry about designing around all these corners, or be willing to sell or basically lose parts, which means your prices are going to go up. So it's kind of a case of careful design versus pricing. Okay, guys, I'm going to stop there. Any questions? Okay.
I don't have any questions.
Okay, if not, guys, have a great weekend, and I'll talk to you guys on Tuesday. Take care.
Thank you, Professor. Have a
Thanks.
good night.
Bye. You too.